Welcome everyone. For today's prep, we're going to start our optimization section. And we're going to start by looking at our first derivative test. So what we're going to see is essentially how we can use our first derivative to help us find and then classify our critical numbers. So we're going to see how we can figure out where our function has a high point or where our function has a low point using our first derivative. So the first part of this process is going to involve finding where our function might have a max or a min. So we're going to find our local extrema. And we've kind of seen a little bit of how to do this already. And it comes down to these special places that we call critical numbers for our function. So we say that a number x equals c is a critical number of the function f, provided one of two things happens. Either the derivative is equal to 0 there, or the derivative is undefined there. Now, there is one technical point here, and there is this extra condition that we need for it to be a critical number. And that is the number has to be in the domain of our function. Because, well, if we're trying to figure out where our function has a minimum or a maximum, well, our function has to be defined there. So why are these critical numbers special? Well, it comes down to an important theorem due to Fermat. So Fermat's theorem here. It says that if our function f has a local max or a local min at some number x equals c, so some location, then either the derivative is 0 there or the derivative is undefined there. So what this theorem tells us is that if our function does have a max or a min, it has to happen at a critical number. That's it. So this really kind of helps us pinpoint all of the possible locations where our function might have a max or a min. So the critical numbers, these critical numbers that we find, these are the possible locations of where our function has a max or a min. And these are all, kind of importantly there, these are all possible locations for where our function has a max or a min. Now, just because something's a critical number doesn't necessarily guarantee that we're going to have a max or a min there. So let's just kind of see a couple graphs to illustrate this. So in each of these graphs, we have a critical number at x equals c. So we have a critical number at x equals c because there's a point on the graph, and in this case, the derivative is 0 there. So for this first one, this is f prime of c is equal to 0, and c is in the domain because there's a point on the graph. So that means x equals c is a critical number. Same thing in the second graph. So in the second graph, there's a point on the graph at x equals c, so there's no missing point there, so it's in the domain. And what we have in this case is we have a cusp, so that means the derivative is undefined. So in this case, we also have a critical number at x equals c. And same thing with the last one. In the last one, our graph momentarily flattens out. We have a horizontal tangent line. So in this last one, f prime is equal to 0 at x equals c. So that means, again, we have another critical number at x equals c. But in the first two, we have a local min at x equals c. So both of these are local mins. These are low points on our graph. Now in the last one, the third one here, this is neither a max or a min. So remember, when we're kind of looking at a graph, you want to think of a max or a min as just a low point, or you want to think of a min as a low point on the graph. So if you were standing at this point, it's basically uphill in both directions. Same thing if we were standing at this point here, uphill in both directions, so it's a min. But if we're standing at this point, So there we are. We're standing there. Well, it's uphill in one direction, but then it's downhill in the other direction. So it's not really a max or a min. But in each of these cases, x equals c is a critical number. So what Fermat's theorem does for us is it gives us all possible locations where our function might have a max or a min, but it doesn't necessarily tell us that we do have a max or a min there. So we need a little bit more to determine what's going on. And that's where the second part of this comes in. So we're going to see, once we find our critical numbers, those are the places, if our function is going to have a max or a min, it has to happen at a critical number. But then we're going to see how to classify them. And the first way to do this is that we're going to look at is with the first derivative test. And the way we use this first derivative test is if we've identified a critical number, well, then we're going to see what the sign of f prime does right around x equals c. So if we have a sign change from positive to negative, well, then our function is going to have a local max. And if f prime changes sign from negative to positive, well, then we have a local min. And if f prime doesn't change signs at x equals c, well, then we don't have either. So it's not a local max or a min at x equals c. So this is we'll call this one our neither case. All right, so it might seem like there's a lot to remember here, but we'll see. Once we have our sign chart, it's really no more work than just figuring out the intervals of increase, decrease here. And that's really what we're going to do. This is going to be very similar to finding the intervals of increase, decrease. Actually, we're going to get the intervals of increase, decrease almost as a byproduct of doing this first derivative test. All right, so we'll save these graphs. We'll look at these graphs in class. But I want to jump down to example 1, just to go over how we actually find and classify these critical numbers. All right, so in this example, we have a function f, and we're given the domain. So the domain for this function is everything except negative 3. And then we're also given the first derivative of this function. So it's x times x minus 1 squared times x plus 3 raised to the negative 3. And before we do anything, let's just rewrite this negative exponent. We've kind of seen one like this before. Let's rewrite this negative exponent as a fraction. So we get x times x minus 1 squared over x plus 3 cubed. So what we're going to do is we're going to use this first derivative to help us find and classify all of the critical numbers for the original function f. So there's kind of two parts to this. First, we want to find the critical numbers. And finding the critical numbers means we need to know. We want to calculate f prime and factor it. That's the first thing. First thing we should do if we're trying to find the critical numbers for a function, we got to calculate its derivative and factor. Now we're given the derivative here, and it's already nicely factored for us, so we don't have to do this in this example. But normally we have to do a little bit of work here. Once we have our first derivative and it's all nicely factored, then we look at where our derivative is 0, and we look for where our derivative is undefined. So we're looking for those two special places. And in this example, we rewrote our derivative as a fraction. So when we're looking for where our derivative is 0, that happens when our numerator is 0. So we're just going to set our numerator equal to 0. And when our derivative is a fraction like this, the only way it can be undefined, or usually the only way it's undefined, is when the denominator is 0. So we're going to just look at the denominator. All right. And let me just get out of the way for a second here. So let's look at our numerator. So when we set this numerator equal to 0, basically we can set each of these individual factors equal to 0. So we have a factor x. We can set that to 0. And then we have two factors of x minus 1. So we can set the x minus 1 factor equal to 0. And then if we solve these for x, we get x equal to 0 and x equal to 1. So it looks like we found two critical numbers so far. And then what about the denominator? Well, we have 3 copies of x plus 3, this x plus 3 factor. So we can set the x plus 3 factor equal to 0. And if we solve that, we get x equal to negative 3. All right, so it looks like we got 3 critical numbers. Now, it's important. Let's pop back up to our definition for critical number. So we're used to just doing these, figuring out where the derivative is 0 or where it's undefined. But there is this little extra piece here, and that is the critical number. For it to be a critical number, it has to be in the domain of our function. So let's check. We found these 3 numbers. So let's start with the first two, x equals 0 and x equals 1. Well, we're given the domain. In this case, we're given the domain of our function. So it's everything except negative 3. So that means 0. 0's in this side, so it's in the domain. And x equals 1, also in the domain. So these are both in the domain of the original function f. And that means these are critical numbers for our function f. Now what about this x equals negative 3? Well, x equals negative 3 is, well, that's not in the domain of this function. It's everything except negative 3. We've kind of removed it. So negative 3 is not in the domain. So x equals negative 3, we call, well, it's not a critical number. It's still important for our intervals of increase-decrease. So we don't want to completely throw this out when if we're trying to do the intervals of increase-decrease. But in terms of actually figuring out where our function has a max or a min, it can happen at negative 3 because negative 3 is not in our domain. But if we were doing the intervals of increase-decrease, we actually still want this negative 3. It's still important. All right, so the first step is to figure out the critical numbers. So that means getting the derivative, factoring it, and then, figuring out our usual things. Once we have all that done, the second part of this is we want to do a sign chart. We want to essentially find the intervals of increase-decrease. So all that work that we saw, how to figure out the intervals of increase-decrease for a function, well, we're just going to redo that here. And so what did we do? Well, we did a sign chart for f prime. So we start by drawing our sign chart, our x-axis. So there we go. And we go to minus infinity in one direction, positive infinity in the other direction. And then we plot all of the x values that we found. So we found negative 3, something was happening there. We found 0 and 1. And what these 3 values do is they split up our x-axis into intervals. So in this case, 4 intervals. And then we just want to identify the sign of f prime on each of these intervals and then figure out, well, what is f doing? Is it increasing or decreasing? And once we have the intervals of increase-decrease, then we can just get a really rough sketch of our graph, what the function f is going to look like, and then we can identify, do we have a max or a min? All right, so, and when we're doing this, it's helpful. We wanted to use all 3 of these values, but it's helpful when we're doing this just to really emphasize which is a critical number and which is a non-critical number. Let's put a closed dot at each of these critical numbers, and then let's put an open dot at x equals -3 because it's a non-critical number. Just to help us remember that our function can only have a max or a min at these filled in dots. All right, so now we want to find the intervals of increase, decrease. And when we do this, we're just going to kind of just repeat the same steps that we did for intervals or doing the sign chart for f prime. So we can write down all of our factors and then put it all together. So let's actually write down our factors here. So we got x minus 1 squared, and then we got x plus 3 cubed. Now here we do have to use our exponents. And then we'll see what f prime is doing, and then ultimately what f is doing. Now for this squared one, whenever we square anything, it's always going to be positive. So we can just go right across, positive. And then for the x factor, that's going to be negative, negative, positive, positive. So again, go back to the increase, decrease if you don't remember exactly how to fill this in. And then for x plus 3 cubed, it's going to be negative, positive, positive, positive. So if we put all this together, a negative times a positive times a negative gives us positive. Negative times positive and positive means negative. And then everything's positive and everything's positive. All right, so let's see what we got. So when f prime is positive, that means the original function's increasing. When f prime is negative, that means we're decreasing, increasing, and then increasing. So what we want to do is we want to classify our two critical numbers. And we could look at the sign change. So f prime is going from negative to positive. But a way to kind of remember that first derivative test. So let's just go back to what it says. When we have this sign change from negative to positive, means we have a local minimum. To kind of help us remember, though, it's easier if you just kind of draw in roughly what the graph is going to look like. So we're decreasing, and then we flatten out, and then we increase again. So right here at x equals 0, we're decreasing, we flatten out, and we're increasing. So if you kind of draw what the shape is going to look like, it's clear it's going to be a local min. So we have a local min at x equals 0. Now what about our other critical number? Well, our other critical number, so we found x equals 0 and x equals 1. Those were our only two critical numbers. If we look at x equals 1, what's going to happen here is our graph is increasing, and then it's going to flatten out, and then it keeps on increasing. So in this case, there's not a sign change. So we have neither max or min at x equals 1. So here we do have a sign change. But over here, there's no sign change. So it's neither. Now, if we're looking at this, if we weren't careful, if we were looking at -3, there we do see a sign change. So it'd be tempting to say that we have a local max at, in this case, at -3, but -3 is not in the domain of our function, so we can't have a max there. So it's still important for these intervals of increase, decrease, but we can't have a max there. All right, so in the next video, or in class, we're going to see how to do this for, functions where we have to actually calculate the derivative. So we'll see you then. Bye-bye.